Okay, hi guys, Mr. Rocco again. This is going to be the second video for the week. So we talked about the Big Bang Theory and the universe in the first part. This is evidence for the Big Bang. Some very important pieces of evidence to prove that the Big Bang Theory actually happened, or the Big Bang happened. First one's Doppler effect. So Doppler effect, you've probably experienced this many, many times. So let's say you're on the street, standing in the village of Rhinebeck, and a fire truck or an ambulance or a police car goes by with their siren on. So this is you standing over here on the street on the right-hand side. As that ambulance or fire truck or whatever comes at you, right, the sound goes up, the pitch, and it gets louder and more and higher frequency. So you'll hear like, and then after the ambulance passes you, now you're over here, the frequency goes down and the pitch goes down, and it'll go, that's Doppler effect, which is affecting two things, light and sound. So it affects sound waves. That's where you hear that up and then down. That's your sound waves. It also affects light, what's called the red shift, and there's a blue shift. Light coming at you is going to turn blue. So that's this one. Blue shift is getting shorter, the frequency. So when light shifts toward the blue end of the spectrum, it's that object is approaching you. The waves are getting compressed. When it's going away from you, the waves are stretching. And that's what creates what's called a red shift. Well, in the universe, right, if we're talking about a Big Bang, and like the last video talked about expansion, right, the galaxies, like I talked about raisin bread, everything moving away. Away would mean stretching. Light galaxies are stretching toward the red, so that's called the red shift. So let me share this video here with you on YouTube.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 108. It's on the Doppler effect. You've maybe heard of that before. It's why a siren, as it approaches you, you'll hear an increase in the pitch, and then it'll actually drop off. But it also could occur if you're moving, and we'll get into that in just a second. So let's say this point here is generating sound waves. They're moving away from that point, and so if you were to listen to them, those sound waves would be hitting you at the same rate, and so it would be a constant pitch. But watch what happens if we move that object from left to right. As it moves from left to right, you can see that the waves in front of it are bunching up. What would that sound like? An increase in pitch. And then behind it, they're actually spreading out. We'd hear a decrease in pitch. You could see the same thing in water waves. The swan, we know, is swimming from right to left. It's swimming to the left. How do we know that? Well, it's generating water waves, and the ones in front of it, you could see, are getting bunched up, and the ones behind it are actually spreading out. So that tells us it's moving to the left. It also has its beak pointed in that direction as well. Now, it's not only sound and water waves, but light is going to do the same thing. And one of the greatest discoveries ever was Edwin Hubble's discovery that wherever he looked out in space, all light seemed to be shifted to the red. We call that a red shift. What did that mean? All the light that he saw was moving away from us. And that indicated we were living in a universe that is constantly expanding. So Doppler effect has these amazing repercussions. And so waves and their observed frequency will change due to motion. And let's say we've got a source of those waves, and then we've got an observer. If the source of the waves is generating waves that move out, they'll be of uniform distribution unless it's moving. So as that source moves, as it approaches the observer, we're going to see an increase in the frequency of those waves. And then as it passes the observer, we'll see a decrease. But it's not only the movement of the source, it could also be the observer. As it approaches the source, it'll hear an increase as it goes towards it, and then it'll actually be a decrease as it moves away. And so let's give me a real example of that. Let's say you're standing there and a car is approaching you. The waves as they come towards you will bunch up. And then as it moves away, we're going to hear that kind of drop off. Why does that occur? As those waves come towards you, they're getting bunched together, and so the frequency is increasing, and that's due to the change in the velocity of that object. And so you'll hear increased frequency, and then it'll actually drop off as it passes you. Now we're going to experience the same thing, however, if we're moving, the observer's moving. So analogy works good for this. Let's say we're generating some waves on the left side, so the waves are moving from left to right. So if you're in a boat, you would feel those waves hitting you. But let's say now that you're moving, so the waves are being produced, but you're moving towards the waves. Since you're moving, you're going to hit them much more quickly, and so we're going to see an increase in the frequency of the waves. Let's say the opposite's occurring. Let's say you're moving with the waves. They're going to hit you at a slower rate, so you would experience a slower frequency, maybe a lower sound if we're talking about pitch. Also applies to light, so as the light is moving away from you, all of those wavelengths will actually be stretched out, and that creates light that's going to be simply moving towards the red. If it's approaching you, it'll actually be moving towards the blue. And so this is an example of that red shift that Hubble saw. Since everything was shifted towards the red, everything was moving away from us. And so did you learn to create a wavefront diagram to demonstrate why as a source approaches you, the wave frequency increases. As it moves past you, it goes away. And also why movement of the observer can do the same thing. I hope so, and I hope that was helpful.
Okay. So as the gentleman just talked about, the red shift. So red shift is a shift toward the red end of the spectrum of light reaching us from distant galaxies. This is indicating that the galaxies are moving away from us, that everything is expanding. Everything's moving away, and that goes back to Big Bang. This is in your ESRT. It's on page 14. It gives you what's called the electromagnetic spectrum. Energy shows two properties, electrical and magnetic properties. And so they take the two words electrical magnetic, put it together, and it's called the electromagnetic spectrum. It's based on what's called wavelengths. So let's say this would be a wave. That's one wave. And if I draw another one, 2 waves, and another one, 3 waves. Each time I draw a wave, right, that's one wavelength. So from there to there is a wavelength. From here to here would be a wavelength, and from here to here is another wavelength. Energy on the left-hand side, you see what it says, decreasing wave. So that means these waves over here, and I can't even really draw them, they'd be microscopic, but the waves would look, really bunched together like this. You couldn't even see them, smaller than that, microscopic. Waves on the right-hand side, increasing wave. The waves would do this. They would stretch out, very long waves. The rule of thumb is the longer the wave length, the less energy it has. So take your radio waves. Radio waves are AM, FM, your cell phone tower waves, all that stuff, satellite, for television like DirecTV. Those waves are not harmful, and therefore they're low energy, and they're long wavelengths. Microwaves, right, that you cook food with, again, they're doing their job cooking the food, but they're not going to hurt you. They used to say microwaves. I remember my mother, don't stand in front of the microwave. You have nothing to worry about. Microwaves are not harmful. Infrared. Infrared is what you and I give off. People give off. So that's heat. Infrared is just body heat. The military will use night vision, which those green image cameras that you'll see in night vision if some of you play video games, like Call of Duty or some of those Black Ops games or whatever they're called. And anyway, those games, they use infrared vision, so heat vision. Visible light, you can see, is right in the middle here. And so visible light then gets broken up into its colors. Violet, right, purple, blue, green, yellow, orange, red. Longer waves are again to the right on this scale, so that's why red's over here. Violets and blues are on this side, so they're shorter wavelength. Then you come out of visible light, because it's in that little section, and you now over here into the really harmful stuff, the ultraviolet, because see, if this is violet, right, that's why they call it, the next thing over would be ultraviolet. Just like on this end, this is red, and then you go to the next thing over, and it's called infrared, see? So So infrared, ultraviolet, which is on either end of the light spectrum. So you got your ultraviolet, which is your UVA, UVB. That's what the ozone layer does. It absorbs that ultraviolet, most of it, to protect us so we don't have issues with skin cancer and things like that. You got your X-rays, which can be very harmful, right? When you go get an X-ray taken at the doctor's office or the hospital, and the technician has to take extra precautions. And then you got your really harmful rays, which are the gamma rays, which will produce extremely high doses of energy. And so when you talk about a red shift, right, that means you're turning colors like violet, blue, green. They're shifting toward this end, the red end, which indicates, again, they're getting longer waves. Longer waves mean they're stretching out, which means it's moving away from you. This was a question on the Regents. It's a typical question. They'll show you this up here, and then this one here is the second picture. What you're looking at is, it shows you spectral lines of hydrogen gas. So if you take, every gas has its own, like, fingerprint, just like you have a fingerprint, right? If you took a fingerprint of your finger, right, that identifies you. Well, gases have their own fingerprint, in quotes. Hydrogen has a bunch of blue lines over here. This would be shorter wave, which is blue, and over here long wave, which would be red, if I go back to that last spectrum I showed you. And so hydrogen has, 1, 2, 3, 4 blue lines over here. This would be toward the red, kind of orangey color. And so what you're looking at here is the standard spectrum for spectral lines for hydrogen. Then, and that's in a lab. See how it says in a laboratory. Now in this picture, you're looking at hydrogen, but this time from a distant star. So you're going from what would hydrogen look like if you're working in a laboratory to what would hydrogen look like in a star that's far away. Notice what happens to these lines. You've got the 4 blue lines here and this 1 orange line here. Notice which way they're shifting. They're all shifting this way toward red, right? Toward the longer wavelength, which is red. And so the question says, compared to the spectral lines observed in the laboratory, meaning this first picture, what is the spectral lines observed in the light from a distant star have shifted which way? So you know it's a red shift because it's moving all the lines, right? Let me clear this so it's not a mess. See how all these lines are here? And I always tell kids, look at which way the lines went in the second picture. And they'll say, oh, they were way over in the corner, Mr. Rocco. Now they're shifting that way toward the red, which means, again, they're moving away, right? Redshift moving longer wave, getting farther away from us. So we're looking at choice 2, the red end of the spectrum, indicating a star moving away from Earth. Occasionally, they don't often do it. They will try to, I don't know if they're trying to trick you, they'll try to do a blue shift. So they'll take all of these lines and these are already toward the blue, but they'll bunch them really close together. So maybe in this picture, instead of having them going that way, they'll have, they got 1, 2, 3, 4, 5 lines. They'll put the 4 lines over here. They'll make them really packed together. This line over here, they'll bring it like over here. So everything looks like it's going that way, which would have then been a blue shift, which would indicate it's moving toward Earth. They don't ask blue shift very often. They usually want you to know the red shift, not the blue shift. This is a lab I used to do. I don't do it anymore. It's a spectroscopy lab. I would give the students different gases, unknown gases, hydrogen, helium, neon, what else, sodium, and they had to look through a prism, and the gas would then give them certain spectral lines. So again, if you look at your hydrogen, you can see that it has these blue lines over here with 1 orange line here. So that was, like, again, the fingerprint for hydrogen. Neon, for example, neon tends to be red. You'd have a bunch of lines over here for neon. And so that would indicate the fingerprint for each gas. So the students had to identify which gas it was based on the fingerprint for each gas. I think I have a chart here. I'll show you. This is just showing you wavelength. So when you measure light waves like blue versus red, you have to use what's called nanometers. A nano is a prefix, means 1/1000th of a meter. So when you're talking about blue light is around 486 nanometers. which is pretty short. As you go this way toward the right, you're getting into longer waves. You're going from 486 nanometers to about 656 nanometers, and that's a red wave of red light. So you're talking a big difference there, a couple hundred nanometers. Now, a nanometer is a very small unit, but in comparison, you're adding a couple of hundred nanometers when you go from blue light and look at red light. So there is a shift and an increase in the size, the length of a wave. Here it is. So this is going to show you different gases. This is flipped the other way, though. The red's on the left side, the blue's on the right, instead of the other way around. But you can see hydrogen. Hydrogen has a lot of purple and a lot of blue light spectral lines, one red. That's it. So if you look through a prism and you look at hydrogen gas through the prism, that's what you're going to see for hydrogen. Sodium, just two simple yellow lines right there. Helium, a few blue, a couple of bluish green, one yellow, and one red. Neons, again, like I said, mostly red, some orange, a little bit of yellow, but definitely down on the red end of the spectrum. Mercury gas is kind of spread out. You got a couple of purple, one blue, a bluish green, a green, a couple of yellow, no red. So, yeah, I don't do that lab anymore, but that was a kind of a fun lab. The kids would be able to try to identify the different gases based on their fingerprint, their spectral lines. Let me skip that. Okay. Second clue. How do we know again, we're going back to Big Bang. How do we know the universe started with a bang? If you think about an explosion. So let's say, an explosion happened, a bomb went off. Usually after the shrapnel, the metal part, there's a lot of dust in the air, right? Smoke and dust that fills in the air. That's where this comes in. So after that initial explosion, that initial Big Bang, remember, it was extremely quick, extremely hot, extremely dense, and all that stuff started to rapidly expand. There was a lot of dust left in the universe that filled in the universe, and it happened to be in the energy form of microwaves. So again, microwaves, I'll go to the chart, are down here. Low energy, not low energy on the scale like radio waves, but that microwave energy filled in the background. So they call it microwave background energy, microwave background radiation. And this was more evidence for the Big Bang. Now, this happened to be picked up by mistake. This was an accident, which a lot of things in science, it's amazing, is, whoops, look what we found. And this ended up being another one of those whoops situations. These two guys here, their names are Arno Penzias and Robert Wilson. This was in New Jersey, 1964. They had this, and I'm going to show you this video here in a sec, this telescope, that radio telescope that picked up frequencies, and they thought it was there was something wrong with the telescope, and the guy will talk about that. They thought there was pigeon droppings in the telescope, and they thought they were picking up noise from New York City. This was right across the river from Manhattan in New Jersey, and so they ended up finding evidence, this background energy that was left over from the Big Bang. So let me show you this video right now.
In 1964, Robert Woodrow Wilson made a startling discovery at this horn antenna with his Bell Labs colleague, Arno Penzias.
The antenna was designed for tracking satellites, in particular the Echo balloon, and they wanted to be able to catch it as it just came up from the horizon and track it all the way across.
But Wilson and Penzias wanted to use it as a radio telescope to explore the galaxy because the antenna had some unusual properties.
It could measure the brightness of a piece of the sky independent of everything else, which most radio telescopes wouldn't do. So we tried to make our receiver work and measure zero for the temperature of the sky, and it simply was not zero. The antenna was producing more noise than we would have expected. What could be causing the problem? There had been an atomic test near Hawaii, but it was slowly decaying, and our signal was not, so we ruled that out. It might be noise from New York City, since we had a clear view of New York City, but what we did was point the antenna at New York City and found that it wasn't particularly hot. There had been a pair of pigeons living in the antenna. The part up there, pigeons liked it. Of course, they had pigeon droppings all over the place up there. So one day Arno and I got up there with a push broom and a bucket of water, and we cleaned it all out. But it didn't make much difference at all. So our control experiment never worked.
But then a casual comment by a friend led to a remarkable connection.
We heard about the theoretical work going on at Princeton about a hot Big Bang. Robert Dickey there had been investigating gravity and realized that expansion would cause the radiation to cool, and it would now be microwaves. And they were going to look for that. Arno called Bob Dickey and told him what we were doing in some detail. Bob asked some questions, and then they said they would like to come for a visit. So when the Princeton people came over to see what we had done, we of course brought them up here. The cabin is where all of the measuring instruments were. So we went in there, looked at our equipment, looked at the horn reflector, and realized that we had made the measurement that they were setting out to make.
That irritating noise turned out to be leftover radiation from the origin of the universe, the cosmic microwave background.
But I don't think we understood at all what the implications were, how much could be derived from that picture of the early universe that it presents. Cosmology has tremendously changed in the decades since then. It's a real science, and we know a lot about the universe. Not everything, of course, but there's a remarkable amount of what went on earlier that's actually frozen in that last surface where the microwave radiation interacted with matter.
Okay, pretty interesting stuff, but it was an accident. But turned out to be a critical part of the Big Bang Theory. Actually, old televisions, when you used to change the channel and go from one channel to the next, would have this picture, and it would make a little snow, they called it. That was microwave energy that would come out of your old TV sets, which again is not harmful to you. So the temperature, again, in the beginning was extremely hot, and then again, as you saw in those epics that video, the last video was talking about, you had to go through the stages where the temperature cooled enough to allow protons and neutrons to form a nucleus, electrons to now bond together to create atoms like hydrogen and helium. Again, this happened, it wasn't overnight. Especially the part about atoms, and I think that took thousands, millions of years to happen, and again, billions of years before you started getting into the star situation. If you take the structure of the universe, excuse me, you have your planets, right? Planets like Mercury, Venus, Earth, Mars, etc. make up a solar system. So this is going from smallest to biggest. So planets make up a solar system. A solar system can be part of a galaxy. Ours happens to be called the Milky Way because of the whitish color that you would see across the sky. It has like a milky band that you can actually see. And then galaxies, of course, make up the universe. So you're going from planets to solar systems make up galaxies, galaxies make up the universe. Our galaxy is what they call a spiral galaxy. It looks like a big giant disc, like a CD or DVD, spiraling around. In a rotation. Summer is usually the easiest time to see the galaxy, but you can actually go out on a very clear night in the summer, and if you look stand there and look north-south, so like face east or face west, and what you're looking at is this is the edge of the disk, sort of, and you're looking at it. That is the Milky Way galaxy. And again, they call it the Milky Way because these are clusters and clusters of stars, not just one star. We're talking billions of stars kind of clustered together to give it that whitish band. And again, it's much easier to see in the summertime than it is in the winter. But if you either look due east or look due west, and then you'll see in a north-south direction this whitish band, you can actually make out the Milky Way, which is kind of cool. We are out on the edge of the disk. So our solar system, our sun, we're out here on toward the edge, I should say. The middle, it's called the galactic bulge. This is actually about half the stars that make up our universe, our galaxy. About 100 billion with a B. So about 100 billion stars, that's about half our galaxy, are clustered in the middle here. The other 100 billion are kind of out on the outer edges of this spiral disk. Now, when you start getting into distances, and this goes back to Polaris, when you start talking about galaxies far, far away, Star Wars and things like that, you have to talk about a different unit of distance. You can't use miles to compare how far is it to Polaris, how far is it to the next galaxy, etc. They use a unit of distance called a light year. By definition, light year is the distance light can travel in a year. Light travels at 186,000 miles per second. 186, that's a crazy number. These are like mind-blowing numbers. So light is traveling 186,000 miles in a second. And so what you'd have to do now is multiply that, right? That's an arrow, times 60 seconds in a minute, times 60 minutes in an hour, times 24 hours in a day, and times 365 days in a year. So you got to keep multiplying this number times all of these factors. You end up with a big number. About 6 trillion, just about 5.96 trillion miles is how far light can go in 1 year. And it says here, the fastest spacecraft today travels 315.5 million miles in a year. If you divide how far light can travel in a year, again, a light year, which is 6 trillion, by how far we can go in a year, you get 18,628.2 years. Meaning, if we only travel, right, at the speed we're going at, right, it would take us more than 18,000 years to get to a place that 1 light year from Earth at the current speed. So we're not going to go very far in our space travel, Star Wars, if we're only traveling at the current speed of a spacecraft. We're going to have to be moving again, not even the speed of light, way, way, way faster. And that's why you see in movies like Star Wars when they jump to light speed, or even like the stars all of a sudden look like spaghetti strands and they go past the Millennium Falcon. Yeah, we're going to have to be traveling at those kinds of speeds and beyond in order to get anywhere anytime fast, right? Think of the if a human being lives to 100 years old, that's a good age, but you'll die on the ship before you get to the next galaxy. So we're going to have to definitely be traveling much, much faster than we currently do. And we will. I think we will. I'm not a doubter. I think we will do that. I don't know if it'll happen in my lifetime or your lifetime, but I think down the road, in generations to come, yeah, the ships will get better and faster, and we'll be able to do those kinds of things. We'll have to. This just throws some numbers. So again, remember, 1 light year, 1 Ly, that's a light year, is equal to 6 trillion miles. That's 1. Our galaxy is 90,000 light years across in diameter. We have 200 billion stars in the galaxy. The mass of the galaxy is 1 trillion solar masses. A solar mass over here, by definition, is the mass of the sun, which happens to be 333,000 times the mass of our planet. So the sun is 333,000 times bigger, more massive than Earth, and our galaxy is 1 trillion suns as far as mass goes. We are, right here, 26,000 light years from the center of our galaxy. That's why I said we're out on the edge of the Milky Way. The thickness of our galaxy is 2,000 light years. Again, remember, each one is 6 trillion miles. And this number is just mind-blowing. Not only do we go around the sun, right, every 365 and a quarter days, but our sun, our solar system, we're moving on the edge of this spiral disk. It takes us 225 million years to make one revolution around the galaxy, to go around this disk, to turn, and us to move around it. 225 million years. I think we did it last year. One of my students had asked, how many times have we done it? And so you'd have to take the age of the universe roughly 13.7 billion years old, divided by this number, and I want to say it came out to be about 21 times. Or I think we're on the 21st trip. So we're not, which is very ironic because we're in the 21st century, but it happens to be just the way the numbers worked out. So we're in the 21st century, and we're on our 21st trip around the Milky Way. Kind of cool. This would be one of our neighboring galaxies called Andromeda. It's also a spiral disk, so that's sort of our shape as well. It is 2.5 million light years away. Again, remember, 1 light year is 6 trillion miles. Discovered by Charles Messier in the 1700s. Our closest galaxy to us, right, this is 2.5 million, Andromeda, is called Sagittarius. It's an elliptical galaxy. Elliptical means it has more of an oval shape to it. It is only 65,000 light years away. So Andromeda is 2.5 million light years away, and this Sagittarius dwarf galaxy is 65,000 light years away. So that's the closest galaxy to our planet. Our galaxies can take different shapes. Again, spiral is a very common shape, like our Milky Way. And again, we sit out on the edge of this little part of the disk, part of the spiral. They have these spiral arms. So this is a spiral arm, spiral arm, spiral arm, spiral arm. And we're out on the end of one of these arms. Elliptical, that's again common. And then you have these just irregular shapes. They don't really have any symmetry to them. They just blobs of gases and stars. And then finally, the last thing, we have our types of planets, right? Which, if you go to page 15, it lists the planets in order. The inner planets, right? Mercury, Venus, Earth, Mars. They are what are called the terrestrials. And so terra, and that comes from Latin. Terra means Earth. Earth-like planets. They're mostly solid, very small diameters, very, very dense, right? It lists a lot of this information in the reference table on the bottom of page 15. So Mercury, Venus, Earth, Mars are the terrestrials, because terra means Earth. And then the outer planets are called the Jovians, which actually comes from the word Jupiter-like. So they're furthest from the sun. They're mostly gas with some icy cores in the middle. Very big diameters, not very dense, again, because they're mostly gas. And these are your planets, Jupiter, Saturn. This one, people will say Uranus. No, it's pronounced Uranus. It actually comes from, people always laugh, I know. It comes from the god of the sky. His name was Uranus. And that's where the name came from when it was discovered. William Herschel, I want to say the mid-1800s. And he looked at the planet Uranus in the 1800s, and it had this beautiful blue color to it, reminded of a beautiful blue sky we might have on a nice sunny day, like today was. Anyway, he would see that, and he said, wow, it reminds me of the sky. What is the god of the sky? Uranus, and that's where the name Uranus came from. Had nothing to do with body parts. Anyway, and so you got Jupiter, Saturn, Uranus, and Neptune. Those are your Jovians. And I am done with this video. So I will post these on Canvas. Please watch both of them in their entirety. And then there'll be one assignment to do on the Big Bang. It's called the Big Bang Worksheet. You also have the test to take and a lab. And that is it. I hope you have a great week. And I will talk to you soon. Bye.